Okay, this is Intro to Beam Stresses number 4. Um, and remember that the basic idea of stresses in beams is this. After you calculate the internal loads, the total stress tensor is going to be the stress tensor that comes from the tension, plus the stress tensor that comes from the bending moment, plus the stress tensor that comes from the shear force, plus the stress tensor that comes from the torque. And the way we orient the beams, these two are each going to be X normal stresses only. This one is going to be an XY shear stress. And this one, it depends on where in the beam the point is, but it is going to be a shear stress of some kind. But we don't know what that is. But anyways, so you calculate those individually, you come up with the stress tensors for each individual one, and then you add up those stress tensors to get the total stress tensor. Well, in this problem, we're not going to have any shear force, we're not going to have any torque, so the only things we have to deal with are the tension and the bending moment. All right, well, the problem looks like this. So there's the beam. There's no weight. If there was weight, there would be shear force here. So, nope. And there's a force this way of 4,000 newtons. And then over here, there's a couple, 2,000 newton meters. And those are all the loads acting. So the first thing we have to do is figure out the reactions at the joints. So I'll draw a free body diagram of the whole beam. We have an unknown force vector over here. I'll call that RA. We have the 4,000 Newton force here. We have an upward reaction here. I'll call that RB. And here we have a couple of 2,000 Newton meters. Newton's second law says that RA force plus negative 4,000 0 plus 0 RB is equal to zeros. So we can tell right away that RAX is positive 4,000 newtons. And then the moment equation, this is about the z-axis. Let's choose our about point to be A at the left end. So there's no moment produced by RA. There's no moment produced by the horizontal force because that's the line of action of that force goes right through the about point. RB, this thing has a length of 2 meters. So we have a moment arm of 2, a force of RB. That force would make it rotate counterclockwise around the about point. So that's positive. And then we have the positive 2,000. And that's equal to 0. And so RB is equal to negative 1,000. And that means that RAY is equal to positive 1,000. Okay, so now that we have those external loads, we can calculate the internal loads. We're going to have to do two cuts because there's a point force in the middle. So the first cut is for x's between 0 and 1. We have, what did I say RAY was? 1,000. So we have an upward force of 1,000 and a force in the positive x direction of 4,000. We haven't gotten to the point in the force in the middle of 4,000 yet. So now we just have the internal loads. There's no torque, so there's no external torque, so I'm just going to leave that off. So Newton's second law says 4,000. Oh, I wrote that upward force is 4,000, but it's just 1,000. Sorry about that. Okay, so our force RA is 4,000, 1,000. And then we have plus T minus V is equal to zeros. So T is equal to negative 4,000 and V is equal to positive 1,000. And now we can do the moment equation about the z-axis. The about point, as always on these cuts, is going to be at the left end. So the only things that produce moments are m and minus vx. And that says that m is equal to vx, which says m is equal to 1,000x. Okay, so these are valid for any x's between 0 and 1 meter. Now we'll go to the second cut. So this is for x's from 1 to 2. So here we have the upward force of 1,000, the rightward force of 4,000. Now we're including the middle force of 4,000 the other way. And then the internal loads T, V, and M. Newton's second law says 4,000, 1,000 plus negative 4,000, 0, plus T negative V is equal to zeros. So T for this section is 0, and V is positive 1,000. Oh, that's what we had before, positive 1,000. And now we go to the moment equation about the z-axis. And again, the about point is going to be the left end. And again, all we have is m minus vx is equal to 0. And so m is equal to 1,000x. And this is for all the x's in the range from 1 to 2. Okay, so now that we have all the internal loads, the stress tensor is going to be the stress tensor due to the tension plus the stress tensor due to the bending moment. Let's do that one next. These are the only two we know how to do so far. Plus the stress tensor due to the shear force, plus the stress tensor due to the torque. This we can calculate, this we can calculate, and we know each of those is just going to have an XX normal element. These two we don't know how to do, okay? So we're going to just leave those aside for now. All right, so first let's do the stress tensors due to tension. Well, we know that sigma XX is equal to the internal tension divided by the cross-sectional area. And the cross-sectional area is 1 times 10 to the minus third meters squared. Okay, so for x from 0 to 1, this sigma xx is equal to, so for that first cut, we had a tension of negative 4,000. That's a compression of 4,000. So this is negative 4,000 newtons divided by 1 times 10 to the minus third meters squared. And so we get a compressive stress, that's what the negative tells us, of 4 times 10 to the 6 pascals. And then on the second cut, well, our internal tension is 0, so for x between 1 and 2, sigma xx is 0. Okay, so on that first half of the beam, the stress tensor due to tension is negative 4 times 10 to the 6, zeros everywhere else. From 1 to 2, the stress tensor due to tension is a 0 tensor. And now we can go to the stress tensor due to the bending moment. Okay, well, one thing we have to figure out first is the value of the area moment of inertia. This is a rectangle, and so the formula is 1/12 times the width of the cross-section, 0.02, times the height cubed. Okay, so we got 0.02 times 0.05 to the third, divided by 12. So that is 9.457 times 10 to the minus third meters to the fourth. And now the formula, well, so the formula for the XX normal stress due to bending is negative my over I. Our m over the whole beam, we don't have to split this up because it ended up being the same function over the whole beam. So m, as you go along the x direction, is, what was it, 1000x? we calculated I. The y can go from, remember that y is the distance from the neutral axis to the point that you're interested in on the cross section. So we can think of this xx normal stress as a function of x and y. Okay, those are going to be the parameters that tell us where we have the answer on the beam. And this is going to be negative. I'm just going back to this formula. 1000x times y divided by 9.457 times 10 to the minus third. And I'll do that division. Okay, so this comes out to be negative 1.057 times 10 to the fifth xy. Okay, so what does that mean? That means so for example, if you wanted to find the point, so if this is the beam, okay, and you wanted to figure out what the stress was at this cross section. Okay, so if we'd be at an x value of okay, so this red line here is the x value, and let's say that that's 1.5 meters. Okay, and then say that we want the neutral axis is here. Okay, so let's say we want to know what the stress was at some point that's a distance of 0.01 meters below the neutral axis. Okay, that's where we want to know what this xy value is. Then the xx normal stress for an x of 1.5 and a y of, since that's below the neutral axis, it would be a y of negative 0.01. We can just plug it into this formula. It would be negative 1.057 times 10 to the fifth times 1.5 times negative 0.01. And so at that point on the beam, we have a stress value of so it's a pretty small stress value of 1,585.5 pascals. And to get the total stress at that point, you'd add up the stress tensor that so the stress tensor at that point would be 1,585.5, zeros everywhere else. That's in pascals, which says, by the way, that bending is making it stretch at that point. And then you'd add that stress tensor to the stress tensor that comes from the internal tension or compression at that point, and that would give you the total, well, we still haven't dealt with the shear force, but that would give you the total XX normal stress at that point on the beam. Well, soon we're going to figure out how to calculate the stress tensor due to the shear force. But for now, this is all we can do.